Hello, everyone. Today, we are hosting Kai-Ming Cheng from University of Washington. He's going to talk about his work during his PhD towards safer augmented reality, identifying, evaluating security, privacy, and safety threats in the AR space. But we were just talking before this hour started. He's going to join Meta, PyTorch Edge team. He's going to apply his knowledge on augmented reality, safety, security with Meta's new kind of gadget, Ray-Ban AI or smart wearable devices. And I'm looking forward to seeing his results as a Meta research scientist. So welcome, Kai-Ming. The stage is yours, and thank you for joining us today.
Thank you. All right, thank you, everyone. Thank you, Vishal, for the introduction and for having me here. It's truly a pleasure to present my work with you at Microsoft. So my name is Kai-Ming. I am a final year PhD candidate at University of Washington. I am advised by Francisca Rosner and Tadayoshi Kono. My research focuses on the security and privacy of augmented reality. At the bottom of my heart, I hope to create a safe, inclusive, and trustworthy AR experience for everyone to use. So today, it's my pleasure to share with you some of our work in this space, and I'm happy to chat more later in the Q&A session. OK, so the concept of augmented reality can be traced back to the 1960s. Over the past few years, we've seen great improvements in AR devices, ranging from glass-like frame device to more of a pass-through headset device. Some people may refer to similar concept as mixed reality. So during the talk, I'll be using the term AR to refer to technologies that place virtual content in a user perceptions of the real-world environment. So for the past 2 years, we've witnessed significant adoption of the glass frame as the preferred form factor for AR, driven by their lightweight design for everyday wear and their rapidly advancing capabilities. For example, AR glasses now offering impressive features like live translation, guided user to perform procedural tasks, perform seeing, understanding, and reasoning in user surrounding, and do live streaming in a first-person view. While AR technologies bring great benefits, they also raise fundamentally new and serious security and privacy risks. For example, this is the first medical case report dated back in 2016, document user getting seriously injured from interacting with AR applications. Since then, previous research, including work from our lab, has demonstrated different types of cognitive attacks in augmented reality. These findings also later inspired DARPA to launch a dedicated program focusing on protecting users from such cognitive attacks in augmented reality. On the privacy front, last year, 2 college students demonstrate how they can combine off-the-shelf AR glasses with facial recognition technology to identify people they just encounter on the street. This, of course, highlights significant privacy concern with the adoption of these new technologies. So industry practitioners have proposed various security and privacy mitigations. While these practices are super valuable, they may fall short in addressing the full spectrum of the security and privacy risks. It is necessary to understand the evolving threats to develop a comprehensive protection framework that address both current and future risks as these devices getting more and more adopted. So to systematically view the threats in augmented reality, here is one approach we could systemize the AR pipeline. So on the left-hand side, we have various sensors taking information about the user, about their surrounding, and about the bystanders. Note that here, these sensors need to be always on to perform key AR functionalities. In addition, new sensors like eye tracking and hand tracking are available on current AR glasses. So in our recent published work, we examined the current permission model for eye tracking and hand tracking in the current AR devices. After processing the input data, the AR system could now generate seamlessly realistic output and integrate it in users' environment. However, this level of immersiveness, when used with ill intention, could also introduce cognitive level attack. So we demonstrate such attack and understand the user mental model in our published work in Usenet Security 2023. Finally, the way users interact with AR technology is different than how we interact with a flat screen, like a mobile device or a desktop. In our work at Usenet Security last year, we looked at the attack vector when user is interacting with three-dimensional user interface in augmented reality, and identify potential vulnerabilities in current AR systems. So for the rest of the talk, I will be presenting our paper on the permission with eye tracking and hand tracking and the attack on the 3D UI in augmented reality. So the first work I'll be presenting is user comprehension and comfort with eye tracking and hand tracking in mixed reality. This is a joint work with Matthias Im, Tadayoshi Kono, and Francisco Rosner from the University of Washington. So as we know, today's AR headsets are equipped with a number of sophisticated sensors. These sensors introduce exciting features. For hand tracking and eye tracking, while the concepts themselves are not new, their integration into mainstream AR devices is novel because it presents exciting opportunities, but also new privacy threats. So for example, by combining eye tracking and hand tracking, a user can navigate the AR environment with simply the eye movement and hand gesture. These input can also create an immersive and interactive experience. For example, the image on the left side, the system can capture how you assemble a piece of hardware and document your hand movement. The eye tracking data can help make your avatar appear more realistic in a virtual setting. And lastly, the eye tracking data can also help the system to do all sorts of optimization for, say, improve the rendering and also the power consumption, optimize the power consumption. Despite the potential benefit, existing research has highlighted privacy concerns with regards to both eye tracking and hand tracking data. For example, the data captured by these devices can be used to infer sensitive user attributes, revealing their identity and their interest level. So as millions of users are starting to try out AR devices for the first time, it is crucial to understand the permission design space with these new sensing technologies and how end users understand and perceive such permission. So in this work, we asked these research questions. First, what is the current technical landscape of eye tracking and hand tracking permission in AR platforms? How do users feel about the different platforms' permission flows, and what are their comfort level? How well do users comprehend the permission details, capabilities, and privacy risks? And lastly, what are the key factors affecting users' decision to adopt AR technologies with eye and hand tracking? Yes.
So everything is happening on device, right? There is no cloud.
I will get. So as we see in the different platforms have different ways of processing this, and we'll get to that in the next slides. Okay, so our methodology starts with structured brainstorming to think about the relevant properties with eye tracking and hand tracking. We then evaluate each of these properties on 3 leading AR platforms, which includes Meta's Oculus Quest Pro, Microsoft HoloLens 2, and Apple's Vision Pro. We also examine documentation and privacy policy and build test applications on device. We then designed a survey to simulate users' first exposure to the permission granting process and launched a survey on Prolific in May 2024. We explicitly recruit participants with no prior AR experience in hope to get their first exposure to this permission design process. And lastly, we recruit like 280 participants, and based on our power analysis. So to get to Vitrul's question of what are these, the different design choices made by these platforms, we found that for say, in terms of permission, both Oculus and HoloLens requires permission for a system or an app to get access to your eye tracking data. Vision Pro, however, employs a different and arguably more privacy-preserving data collection mechanism. The eye tracking data will not be available to website, to applications, not even to Apple, as they claim. In terms of data transmission, we found that Oculus is the only platform that collects users' eye tracking data to their own server. And we found that no application can access eye tracking data in the background. For hand tracking, we found that only Oculus enabled system-level permission, and only Vision Pro enabled app-level permission. Similarly, we found that Oculus is the only platform that collects user hand tracking data, and HoloLens support background access with hand tracking.
So can I just ask?
Yeah.
I'm just using the mic because I'm not sure this is otherwise audible. So just to clarify about the HoloLens, so does that mean that apps can, there's really some API that allows apps to read what, like the hand positions or some gestures, or like what kind of API is it?
Yeah. So essentially, for HoloLens, there will be an API to get the abstracted hand tracking data. That is abstract, like a vector representing your hand joint movement in all different axes. And the reason per se, why HoloLens and Vision Pro does not require permission is because they are kind of like built in with hand tracking as their primary way of interact with the device. Whereas for Oculus, they have their controller. So controller is the main way of interaction. And if you want to use hand tracking, there's an additional permission for that. And for app can access data in background, there's also an API for that, and a setting user can toggle on and off. Essentially, that just gives the application the ability to read users' hand, or to read the hand tracking data from HoloLens, and to kind of like maybe invoke some key functionalities within their app. Right, so for example, like the hand tracking can demonstrate the gesture I'm making, or am I doing a pinch, a point, or in the direction of my point, the length of my hand, the velocity, these kind of like abstracted data in that realm.
Cool, thanks.
Maybe someone should lower her hand.
Maybe I'll just ask quickly. That sounds, just the background data access doesn't sound like a good idea. Is it? Doesn't it? Do you see that as a security risk? Or privacy risk?
Yeah. So the question is this a privacy risk? I think it's a functionality, and depending on how user kind of like set their permission, theoretically, there could be a potential risk if a data application is just recording your hand tracking data all the time. That being said, in certain setting, for say like if you want to deploy AR headsets in a factory or more high-risk, like critical context, such setting might be applicable if they want to detect emergent cases.
Thanks.
Cool. All right, carry on. Yeah, so inspired by the differences across these platforms, we designed a survey to simulate users' actual permission granting process. So participants are randomly assigned to evaluate one of the 3 AR headsets with a random order of eye tracking and hand tracking. They then complete a 5-point scale question to understand how well they're informed, how comfortable they felt, followed by a true-false question to understand the system capability and privacy implication. Finally, we ask what are some of the decision factors that would help them feel more comfortable adopting this technology in the future. Yeah, and for the talk, I'll be presenting a few representative responses on the perception and comprehension. For user comprehension, we conducted a series of mixed methods on each independent variable. First, we found that for both Oculus and HoloLens, participants feel significantly more informed on their utility and privacy about eye tracking than hand tracking. The differences for Vision Pro is, however, not significant. Second, users feel more comfortable using Oculus in both eye tracking and hand tracking. We found for HoloLens, user prefer the preference level is similar with Oculus for eye tracking. And finally, we found that users feel less informed about the Vision Pro's data usage and clarity as they are looking at the permission granting process. For user comprehension, we highlight when participants, even though we recruit people with no prior experience, they had good comprehension for eye tracking and hand tracking utility. 100% of our participants answered correctly for key hand tracking core utility feature. However, we found that people are uninformed about their data being uploaded to the system server. For say only less than 1/4 of the participants correctly identify this data transmission model adopted by Oculus. Furthermore, we found that there's an overestimation on how these devices can have access to their raw sensing data. Over 40% across all platforms believe systems contain their raw eye tracking data. In reality, all platforms have done putting great work in protecting user privacy. For HoloLens and Oculus, only abstracted eye tracking data is available. And for Vision Pro from Apple, they had adopted even more strict privacy protection on the eye tracking data. And similarly, we observe similar behavior on hand tracking. In terms of what factors will help them adopt this technology in the future, we observed that people perform information about who will have access to this data and knowing how this data will be transmitted. In addition, we found that this distribution is highly consistent, which may provide insights to adopting of new sensing technologies like wristband in future AR devices. Based on our findings, we provide a few recommendations for each AR platform. For Oculus, we recommended that it is essential to implement an opt-in and opt-out feature to allow user control their data sharing preference. In addition, it is also possible to build on-device model to understand user hand tracking and eye tracking and infer user intention from that, so that keep the sensitive data on device. For Oculus and HoloLens, while they both protect user eye tracking privacy by only provide abstracted eye tracking data, recent studies has shown that even abstracted eye tracking data can also contain risks on privacy or user intention. One recommendation is to limit system capability or adding stronger privacy guarantee. However, while we noticed that Vision Pro adopted a stronger privacy-preserving techniques, people often fail to fully comprehend their implication. We encourage Apple to clarify or clearly explain their privacy-preserving mechanism to enhance overall user comfort and their understanding on this privacy-preserving techniques Apple is adopting. Yeah.
Sorry, you maybe covered this already, but so what exactly is Apple doing to make it more private?
Yeah. So Apple decided that the eye tracking data is not available to application, to developer, to website, even to Apple themselves. I think the way they are doing it is just purely on a or system level that what I only know is the result of like where or if this button is being clicked, but I have no idea on like where the user is looking at before or after. So the way they designed this is to minimize the kind of like exposure of the eye tracking data to any party.
So that means it's basically all done locally on the device. Is that what it is,
Yes.
and in some kind of like secure
Yes.
component or something?
Yeah. Even
Sorry.
HoloLens eye tracking is also done on device.
Mhm.
And there are very good reasoning to expose that data to developer to build certain applications. However, for example, some medical application, they would like to see the user eye tracking data to infer their health level or whether they have certain disease. That being said, if we have this like AR glasses that in the future everyone wear on an every daily basis, such data, even abstracted, can reveal a lot about our interest level, about what we like or not like. So yeah, I would advocate for at least having the option for user to give them stronger privacy guarantee securing their eye tracking data.
Do you think, I guess, how secure is the Apple thing? Like if you wanted to game it and put, I don't know, like if a developer was malicious and they wanted to put invisible buttons all over the place or something, like is there still a way to get that information if you tried hard enough?
I think there are being some recent security work on just the side channel attack on what and a malicious attacker could infer just by even without the explicit abstracted eye tracking data. Like there's other type of data available that people use to refer or side channeling users like attention level. Yeah, I think this is just like on and off or ongoing research on attacking and protecting user identity within this space.
Sorry. Did you finish, Melissa? Or?
Yes, just saying thank you.
Kaiming, am I understanding correctly that this privacy measurements by Apple is implying that there are some utility loss, like they control the applications and the developers, way to design things, and then they don't provide the same variety of applications for? Okay.
Yeah, and as always, it is a trade-off, and it's hard to find one solution that fit for all different use case. So I think there's also some ongoing work on like how do we actually design this permission model, like how fine-grained do we really want? And a lot of them is kind of like tying to like the application or what are the threat model of doing that. And it's just interesting to see different platforms are adopting different behavior and see how people react to it. And I think it is a very actively ongoing space on designing the flow, designing how users react to that. So yeah, I think it's exciting to see how this field evolve. Yeah, we're trying to kind of like provide like a snapshot of what's happening last year and and see how this field evolved. Cool. All right. Yeah, to summarize, we investigated eye tracking and hand tracking for both Apple Vision Pro, Microsoft HoloLens, and Meta Quest Pro. We launched a survey with 280 participants to understand their perception, comprehension, and the decision factor. And we share findings with industry partners to help improve the permission design. The next project I'm going to present with you is when the user is inside the user interface, an empirical study of UI security properties in augmented reality. This is a joint work with my collaborators from University of Washington, and this is a paper accepted by User Security 2024. Yeah, so previously I talked about like the great advancement of AR hardware. In addition to the hardware advancement, we're also seeing a significant growth in the platforms that support AR technologies. For example, each AR device comes with its own SDK, which is designed to facilitate third-party developers to create immersive AR experience. It's very exciting to work on these technologies, but also raise practical questions, which is what are the different design choices made by these platforms and what are their security implications? Just like how security research examines different browsers or IoT device, for this paper, our goal is to provide foundations to systematically evaluate the current AR platforms and SDKs. For this work, we choose to focus on the UI level security properties for augmented reality. So what is augmented reality user interface? Well, here is an app that I like to illustrate this concept. I found this app helpful if you're doing like house cleaning, because I always worry about if I'm missing a spot or not. But with some with this AR app, it can help me visualize, right, where I covered or not covered. So what is the user interface for AR, right? We have the user perception of this physical world. We have the virtual content rendered on top of the real world. We have user interaction with the virtual content. So recent work began to look into UI-related security issues or privacy issues related to user perception of the physical world. For example, previous USIX paper looked into viewers' attack on inferring information about the user surrounding, about the bystander, and about obscuring real-world content. In this work, we consider a threat model where multiple principles might be interacting with AR UI, such as third-party embedded code running inside an AR application. The attacker goal of this third-party code is to interfere on other principles' AR content or their interactions with the AR content. In this paper, we looked at 5 different UI-level attacks, and I'm going to present one as a motivating example. So the example is clickjacking, right? We know about clickjacking, how it appears on a 2D interface like web browser. But what does it look like in 3D? OK, so the attack motivation is to bait user interaction. Suppose you have a malicious third-party application that is trying to maximize its ads revenue. So it's trying to bait user into clicking their own ad. So on the left, you see this dummy red advertisement created by an ad library. On the right, you see this blue box that says, you'll win a free cookie if you click on it. So while the blue box is visible to user, their interaction when interacting with this blue box actually triggered the red box inside. So this is a proof of concept attack we implement on Apple's ARKit, where users' input goes into a different object, even though what appears to them is a benign content. So while this attack succeeds in Apple's ARKit, we are interested in the underlying properties that make this attack happen. So we found that this clickjacking attack is possible because it's exploiting a property we name as same space. For example, when 2 virtual objects are placed in the same spot, which one renders on top? And similarly, when they place in the same spot, which one get users' input? For example, when 2 virtual objects are placed in the same spot, which one appears on top, right? And depending on how the implementation interact with this corner case, if an object is visible, but the object is not the one that gets user input, it enables potential clickjacking. So how do different AR platforms handle this edge case? So to perform a systematic evaluation on these platforms, we propose several metrics to study this property. The metrics are the rendering order, the interaction order, whether the rendering is consistent or flickering, whether the rendering is consistent, whether the interaction is consistent, and finally, are the object that is visible and the object that receives user input is the same object. The way we evaluate these properties is through a systematic investigation. We implement the test cases with native APIs that runs on designated AR device. We also design a test framework, and we open source our test code. We use a state machine to coordinate all the event-driven test steps, and we structure our code in the way that supports future extension to future AR platforms. So after developing the test case, we conducted over 100 trials on each property for given AR platforms to determine to account for potential non-determinism. We run each trial for 5 times. We run on the different spatial location for 4 times, and make sure that each full test cases will run 5 times. We did find, per se, that the experiment for Oculus is inconsistent and would result to different test results depending on user's spatial or their location, which kind of like highlights the nature of when in 3D, your spatial location matters, and that could be like a new attack vector being exploited. So recalling the clickjacking attack we demonstrated, we identify 2 metrics that mapped to this attack, which is the interaction consistency and the rendering interaction consistency. After examining the metrics, the properties, we can see the different design choices made by different platforms. And we found that this attack is possible on Google's ARCore, Apple's ARKit, and Microsoft HoloLens based on the property evaluation. The second property we looked at is invisibility, where we investigate ways for AR platforms to create invisible virtual objects and to hijack the user input. So it's kind of like a denial of service attack if you kind of like put invisible objects in between to kind of like steal user input. Based on our evaluation, we found that all platforms are vulnerable to this attack under different conditions. Meaning there are a lot of ways you can create an invisible object in AR. Some turning their alpha value, some is disabling rendering, or some just can, using customized material to creating certain objects. And it's interesting to see how each platform is also adopting slightly different way of implementation and how such implementation can be exploited to create this kind of like denial of service attack. So the image on the left is a demonstration using Microsoft MRTK, where user view of the victim object, of the red object, in a natural or in a non-adversarial setting, they can kind of move around the red box as they wish. But if we kind of like create a wrapper or transparent wrapper on top of it and disable this kind of like selection, there's no way user can kind of like indicate their selection of the red box because it's being wrapped by a malicious invisible object.
So Kaimin, a question, is this, so these invisible objects, these are a feature, right?
Yes, these are features.
Okay.
Yeah, I think the bugs and features might be the same thing or not, depending on how you view it. The way I see this is it's important to look at these corner cases to figure out like what are the ways you can exploit them, and then build defenses on top of that.
So this one could presumably be used for the same attack with the fake ads too, right? If you made an invisible ad, is that?
Yeah.
So the same thing you were showing before?
Yes. There are different ways you can create attacks, and here we're just showing proof of concept attacks with the property we looked into. So the third property is synthetic input, where we investigate whether AR platforms can separate user input from synthetic input. We found that all platforms lack mechanism for input provenance, which makes them all vulnerable to input forgery attack. For other attacks, please refer to our paper for more detail. So future AR platforms might be multi-app or multi-user, which makes this issue even more serious. Based on our findings, we provide two sets of recommendations. First, we identify how known defensive strategies can be applied. For example, providing improved provenance or apply Z-fighting mitigation for same space property. Another type is to reconsider this 3D spatial UI defense. For example, how do you design iframe for 3D content, or redesign API that prevent third party from overlaying 3D content? In other words, providing some access control on how content are being displayed in space. Our framework can also extend to future AR platforms. We also implement this attack on Apple's Vision Pro and have some preliminary results. And we hope our framework can apply to help future researchers to evaluate other AR technologies. For example, Google's latest XR runtime in collaboration with Samsung and Qualcomm. So our work covers like a fraction of potential challenge within augmented reality. For example, here are some of the open challenges that that includes, how do we design contextual indicator and for bystander to opt out if they don't want to be recorded by AR glasses. How can we enable like safety-aware AR content placement as user is interacting with the same space, interacting with their real world? And finally, how do we deploy a privacy-aware AR experience within this kind of like power-constrained setting? Tackle these problems requires a community effort to work on them collectively. Last October, my co-organizers and I organized a workshop, the first workshop at the AR conference called ISMAR in Bellevue, actually, focusing on AR design with security, privacy, and safety. And this workshop brought over 30 participants from 16 different institutions, demonstrating growth of interest and commitment in this area. Thank you for listening to my talk, and thank you for all my collaborators. I am happy to take any questions. Thank you.
I do have a question. So actually about the previous slide you had, open challenges, right? So I'm curious, do you know any suggestions for these bystander opt-out methods?
Yeah, that's a great question. We run a study to understand the current indicators on the market. And the approach people are doing is you have this like LED light indicator. It's kind of like Alexa or Google Home. When you invoke with it, it has a light popping on. However, I think different lights we still have like unclear or universal definition on what does these lights even mean, because we've seen different colors. Does the color means different things? Or sometimes when you are recording, the lights is not always on for some device. One of the approach we thought about is, can we give like a bystander a control? First, say there's a hand gesture they can make such that it will disable the recording when the AR device is looking into them. And also, my advisor, Franzi, she explored location-based privacy policy so that maybe at some location, the bystander will just be opt-out. But it is still an ongoing research, I think, even for different companies these days. And
can you imagine that, like, I guess the most extreme one is that the bystander really does some physical thing to like cover their face? Or?
Yeah, it's kind of like facial recognition technology where people wear like adversarial, or physical adversarial shirt that kind of like intentionally obscure the facial recognition result. And yes, I think in some research Akai published last year, we found that they found this recording is still not fully socially acceptable. Like people will feel uncomfortable if someone is just wearing this technology and all day, especially, and especially if minors are around. And there has been effort on like doing post-processing, like identifying all the face in the recording and automatically blur them. That's another way. So I think there's like a big design space on how do you want to like design how do you opt out bystander if possible.
Cool, thanks.
Cool.
All right, well, let's thank Kaiming again.
Yeah, thanks for the invitation.